In this lesson, we're going to be talking about how you can combine all of the different rules of differentiation. Now, the first time I was learning differentiation, I was a little bit overwhelmed with the number of different rules that we were being given. And I guess the problem there is, because we're initially spending so much time just calculating random things, it can feel like you're just memorizing a bunch of formulas. But as is the case with anything in life, you have to learn to walk before you can run. Now, in the context of calculus, learning to walk really just involves learning how to actually do the computations. You haven't really seen all the cool things we can do with calculus just yet. So in this lesson, the first thing I'd like to do is to actually put down all of the rules in one convenient place and actually show you how you can combine them to do more complicated calculations. Okay, so the first rule we learnt about was the superposition rule. And it really just says that you can differentiate a sum of functions by differentiating each one at a time. And we can write it like this. So as you can see here, if we start off with some function h of x, and we say it's equal to some constant times f of x plus another constant times g of x, then its derivative, which is h dash x, is just given by a times f dash x plus b times g dash x. So the next rule we learnt about was the product rule, and it allows you to differentiate a product of functions. And the way we do that is we differentiate each function one at a time and add up all the results, as you can see here. So as we can see here, if we have some function h of x, which is the product of some function f of x and g of x, then its derivative is given by differentiating the first function and leaving the second function. Then you leave the first function and differentiate the second function and add the two results together. Now the next rule we learnt was the chain rule, and it allows you to differentiate a composition of functions where one function is substituted into another function. To do that, we differentiate the outer function first in terms of the inner function, and then we differentiate the inner function and multiply it. So this expression over here shows a function composition. We're saying that h of x is what you'd get if you took the output of f of x and then substituted it into g. Then the derivative is equal to what you would get if you differentiated g in terms of f, and then you multiplied by the derivative of f. Now the last rule we learnt about is the quotient rule, and it's useful any time you divide another function by another function. We found the quotient rule by combining the product rule and the chain rule together. So in theory you could avoid ever using the quotient rule, but it would actually end up making your life a fair bit harder. So let me write it down on the list as well. No matter what functions you choose for f or g, these four rules over here work in general, because we proved them without really assuming any particular function. Okay, so if at this point you're looking at these four rules and freaking out a little bit, I just want you to know that I have a video on each one of them, and you probably should learn them before continuing through this lesson first. Now these four rules over here are actually the general rules of differentiation, and they apply to any function that's differentiable. Now, aside from these general rules over here, we also know how to differentiate specific functions. So for example, we know how to differentiate x to the power of n. Now, there is actually one specific case of the monomial derivatives that I do want to show you, which is the case of the square root of x. Now, as you may know, the square root of x is the same thing as x to the power of 1/2, so technically it's just a special case of this formula up here. However, because it comes up so often, I actually recommend that you commit it to memory. Now at this stage we can actually just bring this half down and then subtract 1 from it, making it negative 1/2. Now the presence of this negative over here immediately tells us that we should put this on the denominator of some fraction, so let me go ahead and do that as well. And now we just have to realize that this x to the power of half is the same thing as the square root of x, which we already said earlier. And now we can actually finish this off by multiplying the 1 and the 1 and the 2 and the root x to write this all in terms of one fraction. So this immediately tells us that the derivative of the square root of x is just 1 divided by 2 times the square root of x. And as I said earlier, you probably should commit this to memory, because if you're taking a course on calculus, chances are it's going to come up a fair bit. Now if you look carefully, the difference between the rules on the left and the rules on the right are that the rules on the left don't actually force us to use specific functions. We're just referring to general functions f and g. But the rules on the right actually refer to specific functions. Now because calculus is so useful and it gets used for so many things, basically anytime you see a new function, the first thing you're going to want to do is to find out whether it's possible to differentiate it. Now, as I've said here, there are many other functions that we will learn to differentiate in our further studies of calculus. In a first course of calculus, usually you just learn to differentiate trig functions and logarithms and exponentials. Now, depending on how much mathematics you actually do in the future, you're very likely to meet way more than just these functions are listed here. But usually in a first course in calculus, as I said, these are the main ones that we focus on. And if you're anything like me, I think you're going to be incredibly surprised by the number of amazing things we can do with these few functions. Now, if you've actually been following my lessons on calculus, or any lessons on calculus, I think the most amazing thing about this page is the fact that no limits appear anywhere. And that means it's actually totally possible to, air quotes, do calculus without really referring to limits at all. So this is actually really cool because you can actually use most of these functions without ever needing to look under the lid and figure out where they came from. Now, this is all well and good when you actually know the functions you want to differentiate. However, in practice, many of the times where I've actually personally used calculus, I didn't actually have access to the underlying function that I was trying to differentiate. And therefore, I think you'd be doing yourself a huge disservice by not actually understanding where we got all of these formulas. Now, without further ado, let's actually work through an example together to see how we can combine these rules to differentiate something a little bit more complicated than the things you've seen so far. Now this here is actually a real monster of a function. I'm really throwing you right into the deep end with this one. However, by methodically working through this derivative with me, I think you'll come to see that it's actually not as complicated as it seems. Now for starters, let's just go ahead and differentiate both sides. Now this is probably something you're pretty used to. You start off with some true statement, and then you go ahead and you apply some operation to both sides. In this case, I'm differentiating both sides. Now for starters, I'm going to go ahead and rewrite this term as h dash x because that's just an alternative notation for the derivative. Okay, so now in the first step, I'm going to be looking at this superposition rule because this a over here is kind of like this 7 and this b over here is kind of like this minus 3. So I can go ahead and apply the superposition rule to this whole term to rewrite it like this. Okay, so now the next thing to do is to look at this term over here. And I notice that I can easily differentiate this term over here. So I'm going to go ahead and do that. Now, by now, you've probably seen this enough times to feel like that was easy enough. But, of course, you're not here for the small fry. You're here for the star of the show. How are we going to deal with this guy? Okay, so looking at this on the highest level, this is just a quotient. You have some function at the top and another function at the bottom, and you're dividing them. So let's go ahead and apply this quotient rule directly. Okay, so it looks like things got a little bit wild there, but it's actually not so bad. Let me just walk you through the steps. The quotient rule tells us to differentiate the top, leave the bottom, then leave the top and differentiate the bottom. And that's exactly what we've done. We've differentiated the top, we've left the bottom, and then we've left the top and differentiated the bottom. And then after that, we're told that we should square the bottom, and that's exactly what we did over here. We squared the bottom. Okay, so we can actually simplify this a fair bit, so let's do that. This part over here, we can just say that the square root and the square just end up crossing each other out. Okay, so now it's probably a good idea to take this term and put it underneath the 7. If we do that, then we won't actually have a fraction over here at all. Okay, so now it looks like things are finally starting to clean up, at least just a little bit. So now the next thing we're going to do is we're going to take these two derivatives over here. Let's begin with this first one over here. What you actually notice is that we actually have a function inside of another function. And therefore, whenever you have this, your mind should immediately jump to using the chain rule. So let's go ahead and do that. We're going to differentiate the outer function first in terms of the inner function, and then we're going to multiply by the derivative of the inner function. So I've just gone ahead and pulled this function out so we can do a little bit of work on it. Now, as you can see, from this form over here, we actually covered this up and then pulled the 3 down and turned it into a 2, as we did here. And then we have to multiply by the derivative of the part I covered up. And now finally, the derivative of this part over here just ends up being 1, because the derivative of a straight line just ends up being a constant. Okay, so now we're actually on the home stretch. We just have one more derivative to take care of. So let me go ahead and pull it out as well, and we'll do some work on it. So now if you look at this carefully, this x plus 2 is just a function. and then outside of it we have another function, which is the square root. So this is just begging to use the chain rule yet again. Now, as we said before, the derivative of the square root, which is actually a little bit covered up over here, is just going to be 1 over 2 times the square root of whatever's on the inside. And in this case, whatever's on the inside is just x plus 2. So as you can see, from this form over here, we just did 1 on 2 times whatever we had on the inside, and then we have to multiply by the derivative of the inside. Now, as we can see, the derivative with respect to x of this term over here is just going to be 1. So we can go ahead and rub this out and replace it for the number 1. And now, because we found that the derivative of this term is equal to this term, we might as well return it to its original place. And now if I can, I'm just going to go ahead and make a little bit of a simplification by taking this term and putting it on the numerator of this term. Now honestly, I'd forgive you if you felt like this was way too much work. Indeed, the first time I saw questions like this, I definitely felt like that was way too much work. But the derivative of h of x over here is this giant expression that we just found here. Now by practicing this a fair bit, you won't actually have to write out all the steps that I wrote. The ones that I've got left over here are actually more than sufficient. But again, that depends on the particular course in calculus you're taking. Now, when I was first learning this, I was making a lot of mistakes. I just kept getting one of the steps wrong somehow. Eventually, I figured out that the source of most of my confusion were these rules over here. I just kept getting them wrong somehow. So, what I ended up doing was, I ended up rewriting them in terms of my own notation that made things a lot easier for me. And I hope that by showing it to you, it might actually make things a lot easier for you as well. Now, at the risk of actually leaving you on a cliffhanger, this lesson is getting a little bit long. So if you'd like to actually see my way of actually computing a derivative like this one, you'll have to tune in for the next part.